Hey, what's going on? I'm David, and today I wanted to show you an interesting way of decoding a digitally encrypted message using light instead of a computer.
For my project, I devised a way to do something kind of fun and novel. My project lets you instantly decode a digital one-time pad with no computer on the receiving end. Instead of using electronic logic gates, my demonstration decoder screen uses pixels that are each optical logic gates. Now, admittedly, a computer is still involved, specifically in the creation of the printed transparencies. I used a spreadsheet to first draw the picture, to encrypt it, and then format it to print out as a transparency. As deceptively simple as it looks, this craft project is actually decoding a cryptographically unbreakable cipher, the Onetime Pad, and it's doing it instantly by processing digital information using light in parallel with no electronic computer involved. A little history. The Onetime Pad was invented in the 1880s as a way of securing telegraph messages. It was later adopted for wartime use by Germany, Russia, and the United States for sending secret messages when they knew others were listening in. The most familiar version of the Onetime Pad encryption method is credited to the American cryptographer Franklin Miller, who invented it in 1882. The system works basically like this. Okay, let's say you are a secret spy being sent behind enemy lines. You take with you a pad of paper that contains pages and pages of completely randomized letters. An identical pad of paper stays behind at headquarters. Now let's say you've obtained some strategically important information that you need to communicate back to base. You know any transmission you send could be picked up, and you want to make sure they don't know the contents of your message. Time to pull a page from your Onetime Pad. Each page is basically an encryption worksheet. Begin by writing your secret message at the top. Is moose and squirrel. No spaces or punctuation. It's very basic. Notice how each letter of your message has a corresponding letter key. To encrypt your message, all you have to do is add them together. Onetime Pad encryption uses a special kind of addition called modular addition. Modular just refers to a system that repeats endlessly over and over like a loop or a circle. The easiest way to do modular addition actually is with a handy little modulator wheel like this. The modulator is really just two disks containing the alphabet printed in a ring. The inner ring can be rotated to match up differently against the outer one. A mod 26 wheel just means there are 26 different symbols and 26 different possible positions you can cycle or modulate through. So you use the wheel to encode the message one letter at a time. Begin with the letter I. Notice the key letter is C, so we set the arrow on the inner disk to the letter C on the outer disk. Now all we do is find the letter I on the inner disk and see what it becomes on the outer disk. I becomes K, so we write K in the cipher line. We just performed a modular addition of I plus C. Okay, now on to letter S. Set the wheel to the key of P, and S becomes H. Write it in the cipher line, and so on. Keep doing this until the entire message is encrypted. You can now safely transmit the coded message from the cipher line without fear of it being decoded. Just remember, you need to burn that page of the Onetime Pad so it isn't discovered and so you can't accidentally reuse it. Back at headquarters, a desk agent will decrypt the message by pulling the identical worksheet from the duplicate pad. See? They have the same key on the worksheet. Next, they fill in the cipher line. To decode a letter, they set the key the same way you did, but they read the disk from the outside to the inside, just the opposite of what you did to encrypt. So let's see. The key for the first letter is C, so they set the wheel to C. Then they find K on the outer disk and look inward. K becomes I. And then they just keep performing this logical operation, letter by letter, and voila, the message emerges. Is moose and squirrel. So that's Onetime Pad encryption for text messages. It worked, but it was cumbersome and required a lot of busy work by hand for even short messages. World War II brought cryptography into the computer age. Instead of using 26 symbols for the whole alphabet, however, computer systems use just two symbols, 0 and 1, binary. Instead of starting with written text, imagine just starting with binary information. We can only write 1 or 0. The key is also binary. And we can do modular addition the same way. It's just that now we use a mod 2 encoder wheel instead of a mod 26. If the message is 1 and the key is 1, then the message becomes 0. Moving along now, if the message is 1 and the key is 0, the message stays 1. The entire cipher gets filled in the same way and gets decoded with modular math on the other end. Here's the cool thing about binary math, though. The whole situation is simple enough to represent with a neat little truth table, no wheel involved. A truth table shows exactly how a logical operator works in terms of its inputs and its outputs. You can see every combination of input on the left, and then what the output would be on the right. To use the table, just look for the combination of inputs, and it tells you the output. If you ever got into computer science or electronics or formal logic, you might have seen different types of logic operators before. There's and, or, not and so on. Each kind has its own symbol and its own truth table. If you look through all these different tables searching for the one we've been using for our secret messaging, you'll be pleasantly surprised. Hey look, here it is. Same truth table. What we want is something called the exclusive OR gate, or the XOR operator. How do you like that? It's actually a thing. The first person to figure out that you could perform the mathematics of a one-time pad using the XOR logic operator was an AT&T Bell Labs engineer named Gilbert Vernon. He received a US patent for it in 1919.
Gilbert Vernon's invention of doing this with logic gates was revolutionary because it took the long, drawn-out hand process of encrypting and decrypting a message and made it logical, and then because it was logical and sort of mechanistic, it made it something that could be done electronically. It laid the foundation for doing cryptography with computers.
Today's computers perform logical operations at a rate of billions of times per second, but the foundations for the techniques we use today for sending ultra-secure messages date back to the early 20th century. My project lets you instantly decode a digital one-time pad with no computer on the receiving end. Here's how the decoder works. Each pixel of the screen has a tissue paper diffuser on the front. Behind that is a square tube, and then space for two side-by-side transparency windows. The encrypted message and the key are both printed the same way on transparency sheets. Each pixel of the key and each pixel of the encrypted message is made of two side-by-side windows, a left half and a right half. The pixels are encoded like this. If the left hand is clear and the right is dark, it represents a 1. If the left is dark and the right is clear, it represents a 0. Now we can do logic between the encrypted message sheet and the key sheet by overlapping one double pixel with another. For instance, if you overlap a 1 with a 1, then light can shine through the left side. If you overlap a 0 with a 0, then light can shine through on the right. Both instances make the entire front pixel light up because there's a way for soft light to shine through and onto the diffuser. If, however, you overlay a 1 with a 0 or a 0 with a 1, both the left and right halves are dark, and the overall pixel is dark. If you make a truth table of this optical logic gate, it looks like this, similar to the XOR gate but inverted. The screen I made actually does not use XOR logic gates like Gilbert Vernon's patent. Instead, it uses XOR's inverted cousin, the XNOR, or exclusive not OR. The cool thing about it is that it works logically the same way. It's just that my message, which I created in a spreadsheet, comes out with inverted color values. Here's the spreadsheet that I used to create the hello image. This is where I drew the message using only 1s and 0s. Here's where I generated the random key. Notice it's the same exact number of cells. And here's the result after performing an XOR operation between the two. The encrypted message then gets copied into a template spreadsheet that formats the cell's height and width into the two side-by-side subpixel format. I printed one sheet that is the message and the other that is the key. You can see, just by sliding them around on the table, how the subpixels line up or block each other depending on where the information is encoded.
Well, so there you go. You can put this little sandwich of layers together, shine some light through the back, and see some cryptographic magic appear right before your very eyes. I hope you enjoyed this video. I had a great time making it. Please share or like and comment if you have anything constructive to say. Also, if you're interested in playing with this technology, specifically this exact thing, I've posted the 3D print files and also the spreadsheets that I use to generate it. Look for the link below the video. Have a great time. Keep creating stuff, and I hope to hear from you soon. Thanks. Bye.